Okay, so here we're going to cover the content of what's called Module 6 for the uploaded material for this course. And this is a module introducing the gradient operator. And this is probably, as we say in the notes, probably the first real vector calculus thing that's really new in this course. And this is very emblematic of vector calculus, the gradient operator. It is an operator that will turn or convert a scalar function into a vector function. That's not its purpose. Its purpose is something more physical, but that's the mathematical effect of it. It's got a scalar input, and then we have, as a result, a vector output. And so we're going to define this. This is a very short module, and then we're going to have a couple other ones where we do some examples, because that's the pretty easy way to see this. It's a simple introduction. So the gradient operator is defined like this. Okay? So usually we write it as this symbol, and this symbol by itself is often called nabla. Sometimes it's called del. When it's used as a gradient operator, we will say grad f. We'll see that in a minute. But it can have different names in different contexts, and it'll sort of be obvious when we do it. So by itself, it's not anything. It's an operator, and it doesn't really doesn't mean anything until we apply it to a function, which we'll see. So this is really, it's like an upside down triangle. I write it with a little underscore underneath it to remind myself that it's sort of a vector. Okay, so we have unit vector I, and then the partial derivative with respect to x, plus unit vector j, partial derivative with respect to y, partial unit vector k, partial derivative with respect to z. So this is the del operator, or the gradient operator, I should say, in Cartesian coordinates. It has a different form in other coordinate systems, and we will probably cover that later on in this course. So as you can see, it's got components in a sense, but it doesn't have anything yet. These are derivatives that haven't been applied to a function yet. So normally the way this happens is you would say something like this. You say, I have grad f. Okay, so we write that symbol for triangle, underscore, that's how I write it, and then some function to be determined. In general, this is a function of x, y, z. So it could be temperature at every location, x, y, z in this room. That could be what f is. Okay, or it could be the potential, the electrical potential, everywhere in the vicinity of a charge. Okay, so it's not a vector, it's just a scalar valued function. Okay, so when we calculate grad f, that's how we say this, grad f, we're saying that we have now the partial of f with respect to x along the x direction, plus the partial derivative of f with respect to y along the y direction, plus the partial derivative of f with respect to z along the k direction. Okay? And so what you have when you're done is you had a scalar function to start with, you take the gradient of that, and you end up with a vector. Okay? Now, a couple notations that we'll get to just before we do a first example is sometimes you'll see something like this written. You'll see bracket grad f sub x. So this means, really, it means the partial of f with respect to x. It's just the x component of the grad vector itself. I don't use that notation a lot, but we could. Obviously, the gradient is extracting for us the variation in a three-dimensional function along each of the axes one at a time. So the x component of the gradient is the variation of f with respect to x alone, and the y component of the gradient of f is the variation in f along y, similarly for z. So in this sense, it is the slope of f along x, and then the slope of f along y, slope of f along z. So it measures or calculates for us, or maybe represents for us is a better way to say it. It represents the local slope of that function with respect to each coordinate separately. And that's kind of why it's a vector. you could have some variation in x, some variation in y, some variation in z, and the combination of those things is some variation in 3 space that has some direction, and that would be the vector. Okay? So really simple example would be if we just said, okay, let's just let, this is about as simple as it gets, let g x, y, z equal x times y times z. It's just a made up function. We don't have to always write g as a function of x, y, z. We do it at this stage because we want to be clear about what's depending on 3 variables, what's depending on 2. But soon enough, we'll kind of stop that. It's obvious if I just said g equal x, y, z, that g is a function of x, y, z, right? But we'll write this for a while just to be super clear. So the gradient of g, right, would be, the way we really write this right, I die x plus j, I'm doing this really slow, k die by z times, and it operates on x, y, z. So I'm writing this really slowly as if we were doing this operator. So this is the operator operating on this function. And then you just bring it in, so this would become I die x of x, y, z plus j die y, x, y, z plus k, derivative with respect to z, x, y, z. Okay? And then we say, okay, these partial derivatives, y, z are a constant, x is this. This just becomes y, z, I plus x, z, j plus x, y, k. And that would be the gradient of g defined in this way. So super simple. Little thing, why do I write the unit vectors on the left-hand side of the gradients up here, and then once I start to do it, when I get my final answer, I draw the unit vectors on the right-hand side of the expression. There's no particular right answer to this, and some of the modules discuss this a little bit. It's kind of, I don't know, I'd call it very typical when you have an operator to keep them on this side, and then once you've done the operation, when you're done, you simplify and you bring everything to the left-hand side of the unit vector. Everything to the left-hand side of the unit vector. It's not wrong to write this as I hat yz. What would be weird is don't write y I hat z. That's weird. It's not, I guess it's not totally wrong, but that would be a weird thing to do. Okay? Now, one other little thing you can actually sort of see, and this is kind of the last point we'll make regarding the gradient, and this is in the spirit of, like, if we think about this more physically, not just mathematically, is, almost like unit analysis. So if x and y and z are actual dimensions in real space, they each have units of meters. So x, y, z would have units of meters cubed, right? Something like a volume. So g, the function g, has units meters cubed. So the slope of g with respect to distance, or the derivative of g, no matter what direction you take it in, needs to have units of meters squared. Because really, these derivatives are almost like dividing by a meter. So you've got meter cubed and 1 over meter. So this whole thing in the end, the units of the gradient should have units of meters squared. Okay? And of course it does. When we're done, the act of the differentiation removes one of the spatial variables. You end up with just y times z, which is meters squared. xz meters squared. The unit vectors do not have units. They don't carry meters with them. Okay? They are unitless in that sense. Okay, so makes sense. We started off with meter cubed, we end up with meter squared. It's not always super easy to do that kind of thing, and if we have transcendental functions, like if the components are e to the x times sine y, none of that has units, right, outright. So this isn't always super helpful, but there are times where it should continue to make sense. Okay, so that's all there is to it. That's the simple process. It's the definition of the gradient operator. This is the formal application of the gradient operator applied to f. So grad f is this expression here. Give a sort of simple example. And this calculating the gradient of things is something we will do. It's a pretty simple step. You can do it in one step if you really want. We'll look at harder problems, a little bit harder, but in general, the gradient operation is one of the easiest vector calculus operations. The next ones we do will be a little bit harder, not a lot, but we will definitely build on this in the modules to come.